Today's video is on molecular formulas. It's very similar to empirical. We just got one extra step to add at the end. So, empirical formulas that we were solving for in the last section, they do not always indicate what the actual compound is. They just give the formula in its simplest ratio. Okay, it's just the simplest ratio of one element to the others. A molecular formula, though, is going to be a chemical formula which specifies the actual number, not the smallest ratio of atoms of elements of each element in one molecule or formula unit of the substance. So, for instance, we could have solved one in the previous section, and it could have come out HO, which would have been the empirical formula, 1 hydrogen to 1 oxygen. But now we'll see there's a way to figure out the molecular formula, so what the formula actually is. So it could be like H2O2 or H3O3 or H4O4. And we're going to see how to do that. It's very, very similar to solving for empirical formulas, just one step. So if you were comfortable doing those, this is just one little more thing to do. Okay, so we'll do this problem first. Determine the molecular formula of butane, given that its molar mass is 58.14 grams per mole, and it is 82.6% carbon and 17.4% hydrogen by mass. So really, everything in steps in order to solve this is the same except for the last one, right? We begin by finding the empirical formula of butane. So we assumed 100 grams of the compound so that we could turn those percentages into grams. We'd convert the grams into moles. We would divide by whichever one was the smallest amount of moles, and then we would look at our ratios there and figure out what the empirical formula was. The only thing that we have to do in addition now is we're going to use the molar mass given to us in the problem to find the molecular formula. So it's just one more thing to do at the very end. Now we're going to turn grams into moles. So we're going to take the 82.6 grams of carbon, divide by the 12.01, and we get 6.88, right? Remember, we can turn the percentages into grams because we are assuming 100 grams of the compound. And the second one, 17.4 divided by 1.01 is, let's see here, 17.23 moles of hydrogen. Okay, so now we have things in moles. Next step is divide them by whichever one is the smallest amount of moles. Well, 6.88 was the smaller amount, so that's going to give us 1 mole of carbon, and then the 17.23 divided by 6.88 gives us the 2.50 moles of hydrogen. And from there, we're going to find our empirical formula. Okay, remember, we've seen this before. You've seen a couple of examples where we can't have this fraction as part of our formula. It's not CH2.5. You can't have half of a hydrogen atom. So in this case, we're going to multiply by some whole number to get rid of the 2.5. Well, we're going to multiply by 2 because 2.5 times 2 gives us a whole number. And so if we multiply everything in the formula by 2, we wind up with an empirical formula here of C2H5. And really to this point is everything that we've done before. So this is just like section 3. We haven't done anything new yet. Okay, so now to figure out what the molecular formula is, what the real formula of this compound is, we need to figure out the molar mass of the empirical formula. Okay, that's what we need to solve for. So our empirical formula was C2H5. So right here, solving for the molar mass, 12.01 grams per mole times 2 for the carbon, plus 1.01 grams per mole times 5 for the hydrogen. We get a molar mass here for the empirical formula, okay, EMP, equaling 29.07 grams per mole. We're going to use that. So what do we do with it? Last step here, compare the molar mass of the empirical formula, okay, the one we just calculated on the previous slide, with the molar mass of the molecular formula. Well, where is that? Right there. Okay, it's given to you in the problem. The good news is, if you've done everything correct up to this point, this part should work out really nicely into a very convenient and obvious whole number, or pretty darn close to it, to the point where you know what it's supposed to be. Remember, these are measurements, so it's not going to be perfect every time. But what we're going to do is take the molar mass of the molecular formula given to us in the problem, 58.14 grams per mole, and divide by the molar mass of the empirical formula, which we just found on the previous slide, 29.07, okay? And that one is exactly right. The top one is twice that of the bottom. So that's giving us the ratio here that the molecular formula is twice as much as the empirical formula. So what we need to do is take the empirical formula and multiply it times 2, and that would give us the molecular formula. So we had C2H5, this was the empirical, right? So we figured out first, okay? And when we multiply everything in there by 2, we get C4H10. So the molecular formula of butane is actually C4H10, okay? So really all we had to do, in addition to what you already know how to do, is find the molar mass of the empirical formula, and then take the molar mass of the molecular formula divided by the molar mass of the empirical formula, and it gives you some pretty nice whole number ratio, okay? And then you just multiply your empirical formula by that number, and that's your answer. So it's really nothing too difficult to do if you're already doing pretty well. Okay, so this is one more just for practice. I'm going to solve it on the next slide here. It's stearic acid. It's a saturated fatty acid containing carbon, hydrogen, and oxygen. Its molar mass is 284.54. It's composed of 76.0% carbon, 12.8% hydrogen, 11.2% oxygen. What is the molecular formula of stearic acid? So right, this is just our steps to solving it, and we're going to do that on the next slide. Okay, so first thing we want to do, we assume 100 grams of the compound so we can start turning things into moles. So we have 76.0 divided by 12.01 for the carbon, and I'm going to carry a couple of extra significant figures through for now because we can do that. 12.8 grams of hydrogen divided by 1.01 grams per mole. And that is 12.6733 and 11.2 grams of oxygen divided by 16. This one's going to be our smallest one. 0.7, pretty much right on the nose. So moles of oxygen. So we're going to divide them all by 0.700, 0.700. Divided by 0.700. Okay, the bottom one's just going to give us 1, so we know we're going to have oxygen being 1. The top one, 6.32881 divided by 0.7. Okay, that gives us 9.04. Looks like that's pretty close to 9. 12.6733 divided by 0.7. Okay, and this looks like it's going to be pretty close to being 18, okay? Now, if we're doing this correct, it actually should work out nicely because, like we saw before, the molar mass of my empirical formula should be some sort of, right, or my molecular formula should be some sort of multiple of the empirical's molar mass. So we'll see if we're correct on this, okay? So the molar mass of the empirical formula, we have 9 for the carbon times 12.01, plus we have 18 times the 1.01 for hydrogen, plus we've got, let's see here, 1 for the oxygen times 16.00. And all that put together, (142.27 grams per mole. So we've got our empirical formula molar mass. We'll take the molecular divided by the empirical. This is 284.54 divided by 142.27. And some of you can probably already see mathematically that's going to work out to give us exactly 2. So that means that my molecular formula is twice that of my empirical formula. So instead of C9H18O, which would have been the empirical formula. Okay, my molecular formula is going to be double that, so it's going to be C18H36O2. Okay, so we can get some of these larger numbers here, and some of the ones for the homework you'll see will have that as well.